So today we're going to be talking about something interesting, which is the determinant. So maybe the way you want to think about this at this point is that, and this is not really the right way of thinking about it, but you can think of it as a way of associating with the matrix a number that indicates if the matrix is invertible. Okay, so I mean, this is not really this is not everything about the determinant. This is just one part of the determinant. Okay, but maybe at this point you can think of it like that. It's a number that tells you if the matrix is invertible or not. Okay, but it actually tells you more than that. So I'm going to erase this. I don't like this. Okay, it's gone. Okay, in any case, we're going to associate to each matrix. We're going to associate some number, and this number is going to give us some information. Okay. Really, the way you want to think about the determinant is that it's a number that indicates how the matrix expands volume. That's actually a better way of thinking about it. A number that indicates how the matrix expands volume, expands or compresses volume. Okay. So, right, if the determinant is 0, that means that the matrix collapses volume. Okay, that means that the matrix collapses volume, and that should tell you something about its invertibility, right? Can you invert something that collapses everything down to a single point? No, right? Because how do you get back? How do you get home again? If you take an interval, say in R1, and you multiply it by the number 0, well, you've contracted it all down to just the 0 point. Now tell me how to get back to my original interval. You can't, right? But if you multiply the interval by something non-zero, then you can reverse it, right? You can reverse it, right? Even if I multiply it by 2, I've expanded the interval, right? Right. So if I take 0, 1, say, and I multiply everything in it by 2, right? I multiply everything in it by 2, and I get the interval 0, 2, right? So this 2 does something to the interval. It expands the volume, expands the length of the interval, right, by some number, right, by some number, the absolute value of 2. And just in the same way, the matrix will expand the volume of a region to which is applied by some number, the determinant, right, and that tells you about invertibility. Okay. Right? If your determinant is 0, you're not invertible. If you're non-zero, you're good. So the only time you're not invertible is if you get a 0 determinant. Okay, so that's really the right way of thinking about the matrix. I'm sorry, about the determinant. Okay, 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 and that's why you will or you have already seen the determinant occurring in the change of variable formula in multivariable calculus, as if you've seen it before. Okay. Okay, so heading towards the definition of the matrix, we start off with something called the minor matrix. I'm sorry, heading towards the definition of the determinant, let's first define something called the minor matrix, minor matrices. So you have an n by n matrix, you have a square matrix. We define the ijth minor matrix minor matrix and let's call it Mij for m for minor, to be the n minus 1 by n minus 1 matrix that one obtains by excising A's ith row and jth column. Okay, so the ijth minor matrix, right? You have some matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, and right, if I write M12, I mean that when you excise the first row and the second column, and you end up with a 2 by 2 matrix. Right? You end up with a 2 by 2 matrix, right? A square matrix of size 1 less than the previous one. Okay, so that's what's called a minor matrix. Okay. And now we can start to define the determinant. We're going to give this definition inductively. So we're going to first start from the 1 by 1 matrices. So if A is a 1 by 1 matrix, then the determinant of A, right, which we will sometimes denote as det A or absolute value of A, is just going to be the value of the entry. Right? A is a matrix consisting of one entry. The determinant is just going to be that entry. It's just going to be that number. Okay. So for a 2 by 2 matrix, so A, sorry, in general, not just for 2 by 2. So if A is an n by n matrix with n bigger than or equal to 2, then we define the determinant of A as it's going to be a little bit funny, but like this: A11 capital A1 plus A12 capital A12 plus A1n capital A1n, where I didn't explain what these capital A's are. Capital Aij is -1 to the I plus j times the determinant of the ij minor. And these things are called the cofactors, ij cofactors. Okay. Okay, so take a look at this. What does it say? It says that the determinant of A is going to be the entries of the first row multiplied by some power of -1 times the determinants of the minor matrices, of the corresponding minor matrices. Okay, so it's just going to be some combination of minor matrices, determinants, and the first row's coefficients. And the thing you want to notice is that this is an inductive definition. You see that the determinant of an n by n matrix is defined using the determinant, right? So you might think that's sort of problematic, right? An n by n matrix is defined using the determinant of an n minus 1 by n minus 1 matrix. Okay, so this is where the bootstrapping occurs, right? The 2 by 2 matrices are defined in terms of using the definition of the 2 by 2 matrices determinant involves the determinant of the 1 by 1s. Well, the determinant of the 1 by 1s is given. Okay, so then you have the definition of the 2 by 2s, right? The definition of 3 by 3s is defined using the determinant of the 2 by 2s. Well, now we already have the 2 by 2s, so we can get the 3 by 3s, and so on and so forth. Okay, so this is so notice that this is an inductive definition. Okay, so let's just start with some examples. If I look at, say, the determinant of 3, 2, negative 2, 4, well, what does this say? This says I'm going to take A11, that's 3, right? I'm going to take 3, and I'm going to multiply that by negative 1 to the 1 plus 1 times the determinant of the minor matrix you get when you cross out the first row and the first column. And then I'm going to add on to that 2 times negative 1 to the 1 plus 2 times the determinant of the minor matrix that I get by crossing off the second row, the first row and the second column. Right. So I get 3 times 4 minus 2 times negative 2. So it's 12 plus 4, 16. Mia?
And you only do that for the first row?
We'll get to that in a second.
Okay.
Yeah. So yes, that's how we're going to define it. That's how we're going to define it. Right. And in general, if I'm looking at the determinant of some matrix A, B, C, D, some 2 by 2 guy, well, what do I get? I'm going to get A times 1 times D plus B times negative 1 times C. Right? So it'll be AD minus BC if you work it out, if you just go through the definition. Right? This is A times negative 1 to the 1 plus 1 times the determinant of D plus B times negative 1 to the 1 plus 2 times the determinant of C. So the determinants of 2 by 2s turn out to be, this diagonal, the product of this diagonal minus the product of that diagonal. Okay. Another example. I'm taking the determinant of 1, 0, 7, 1, 3, 2, 1, negative 2, 4. Right? So I've got a 3 by 3. You know it's going to be defined in terms of the determinants of the 2 by 2s. So this is going to be A11, A11 times negative 1 to the 1 plus 1, right? Because we're within A11, right? Times the determinant of 3, 2, negative 2, 4, right? Then we get plus 0, and I'm going to write it out even though we don't need to, so we'll get to that 0. So negative 1 to the 1 plus 2 times the determinant of 1, 2, 1, 4, plus 7 times negative 1 to the 1 plus 3 times the determinant of 1, 3, 1, negative 2. Right? You have this guy, and then you have negative 1 to the 1 plus 1, because we're dealing with the 1, 1 position. And you multiply it by the determinant of this. Right? Then you add on this guy times negative 1 to the 1 plus 2, so that's that's a -1, times the determinant of this matrix, the remaining minor matrix, plus 7 times -1 to the 4 times the determinant of this minor matrix. Okay. Right. So that turns out to be 1 times 16, right, plus 0, so minus 7 times -5, right, so 51. Plus 7,
yeah.
sorry. Right, so that's -19. Okay, and if we got a 4 by 4 matrix, well then we have to, right, we have a 4 by 4 matrix, 1, 3, 5, 7, 1, 0, 7, 1, 3, 2, 1, -2, 4, 5, 3, right? Then we'd have to go through the sort of long and tedious process of taking this times 1 times the determinant of that, this times -1 times the determinant of its minor, et cetera, and we go downwards, right? So this process is called cofactor expansion. Or rather, I should say that this thing is called the cofactor expansion of the determinant. This product here is the cofactor expansion of the determinant. Also called expansion by minors. Expansion by minors. Okay, everyone all right with the procedure? Okay, not particularly demanding. It's just an algorithm that you follow. You notice that if we say, suppose, so Mia asked, can you take an expansion down any row or any column? So let's try it. Okay, so if we take, say, the expansion, suppose we take like this, and we feel like we look at, let's look at 0, right? So we're gonna go down this column. So we take 0 times -1 to the 1 plus 2 times the determinant of 1, 2, 1, 4 plus 3 times -1 to the 2 plus 2 times the determinant of 1, 7, 1, 4 plus -2 times -1 to the 2 plus 3 right, times 1, 7, 1, 2, 1, 7, 1, 2. Right? And so this is 0, of course, right? And then here we get 3 times -3, 3 times -3, and here we get 2 times -5, right? And so we end up with -19. Right? We end up with the same number. Right? In fact, cofactor expansions can be taken down any row or any column, will mysteriously always end up with the same number, the determinant. Okay, so in fact, one could calculate the determinant by going down, taking the expansion down any row or any column. So I'll write that down as a useful theorem. Cofactor expansions down any row or column yield the same value. Namely, the determinant. Okay. We're not going to prove it. if you're interested in the proof I think is not particularly illuminating. But you can find, if you're interested, you can find one proof in a book that I think should be accessible to you. It's by authors named Frawley and Beauregard. So Appendix B. You can see how uninteresting it is by the fact that they relegated it to an appendix, right? It's not. Clearly, they did not want to put it in the book. Right? It's like, for the interested reader, we've put it in Appendix B. Okay, but it's a very useful fact, right? That you can take cofactor expansions down whatever equality you feel like. For example, if I say here is a 5 by 5 matrix, 3, 2, 0, 1, 3, -2, 4, 1, 2, 1, 0, -1, 0, 1, -5, -1, 2, 0, -1, 2, 0, 0, 0, 0, 2. Right? Then, and I say, find the determinant of it, right? Then if you just follow the definition, then you would say, okay, I'm going to take 3 times the determinant of this, and then I'm going to take -2 times the determinant of the 4 by 4. You'd have all these 4 by 4 matrices, right? But using this fact, you say, okay, I'm going to expand along this row, right? So I get 2, right? So the determinant then is going to be 2 times the determinant of this, right? Of this guy, right? And then you say, well, how am I going to calculate the determinant of this? Well, clearly I'm going to use this column, right? So I'm going to take, I'm going to get a -1, right? -1 times the determinant of this thing, right? So I get -1 times the determinant of 3, 2, 1, 0, -1, 1, -1, 2, -1, right? And so that would reduce your work by a lot. Right? Then you'd have this one thing, right? And you'd probably take the determinant. You'd probably expand on this thing, et cetera, et cetera. Right? Okay. So you see that this is useful. Okay. Any questions? Everyone okay? Good. Okay. Okay, so let me ask you a question. What is the determinant of a diagonal matrix? What's the determinant of a diagonal matrix? Say the matrix, it's all zeros except on the diagonal where you have some numbers.
I feel like it's going to be 0.
The product of the numbers in the diagonal.
So you got all these zeros. Right, you got all these zeros down here, you got all these zeros up here.
Then just that. Multiplied by each other.
Right. So what's it going to be? Elena?
The product of the numbers in the diagonal.
It'll be the product down the diagonal, actually. It'll turn out to be the determinant of this diagonal matrix will turn out to be A11, A22, ANN. And you can sort of see that. Let me. What time is it? Let's see. let me ask you to think for about 2 or 3 minutes about how you might prove this by induction. Okay? So try to prove the statement by induction. So remember what you have to do. You have to show that an initial case is true. So initial case is true, and then show that the case for one guy implies the case for the next guy. Okay, so induction on the dimension, right, on the size of the matrix. Right, this is a n by n. It's an n by n matrix. So you're going to induct on n. That is, you'll need to prove it for case n equals 1, and then show that if you have it for the case n minus 1, then you know it for the case n. Okay, so let's just, we can do it together. Maybe for, okay, yeah, so how would you do it? So first you need to show it for the case n equals 1. So case n equals 1, so proof by induction. Case n equals 1, well, right, is what we want to show is that the determinant is just the it's the product down the diagonal, right? But there's only one element, right? Our matrix consists only of one element. So of course, and the definition of the determinant is that one element. So it is as desired. Okay. So case n equals 1 is obvious, right? The determinant of this diagonal matrix is in fact the product down the diagonal, the sole element of that matrix. Okay. So then, so assume the statement is true. for n minus 1 by n minus 1 matrices. I want to show that then it's true for n by n matrices. Right? Okay, well, let A be an n by n matrix. Right? Diagonal. So why does the truth of the n minus 1 case imply the truth of the nth case? Right? We want to show that the determinant of this is the product down the diagonal. Right? Well, the determinant of A is what?
Using cofactor expansion.
You can use the cofactor expansion. You say, okay, this is going to be A11 times capital A11, right? A1, that is to say, A11 times -1 squared times the determinant of M11, right? Right? And then what? Well, what's the size of M11? It's n minus 1, n minus 1. And further, is it a diagonal matrix? Yeah. Right? So M11 is an n minus 1 by n minus 1 diagonal matrix. Right? It's the matrix A22 down to ANN. Right? So by induction hypothesis, how one writes it? Yeah, by the induction hypothesis, we know that the determinant of M11 is going to be the product down the diagonals, right? So A22 to ANN. Right? Because we're doing this by induction, so we assume that the statement is true for n minus 1 by n minus 1 matrices. Right? Well, here's an n minus 1 by n minus 1 diagonal matrix, and so its its determinant is A22. It's the product of its diagonals, right? And thus, the determinant of A is going to be A11 times 1 times A22 times A and N, as desired. Okay. And so what we've shown is that if the statement is true for the n minus 1 case, then it's true for the case of n by n matrices. So the inductive step is proved. It's proved, and so that's the end. So that's the end by induction. Okay, so this is how you would write it up. Okay, any questions about the method or the procedure? So it's just an example. We'll do a couple. It will turn out that in proving properties about the determinant, that proof by induction is pretty handy. And that sort of makes sense because the definition that we gave of the determinant is an inductive definition, right? So you can sort of see that a proof by induction will be useful. Okay, so consequences of the useful theorem. So the useful theorem can be used to imply some properties of the determinant. Properties of the determinant. So again, we start off with an n by n matrix. First off, the determinant of the transpose is the same thing as the determinant of the original matrix. Second, if A prime is obtained from A by interchanging two rows, or it could be two columns, then the determinant of A prime turns out to be minus the determinant of A. So if you take a matrix and you switch two rows, then its determinant will be negative that of the first matrix. And as a corollary, if A has two identical rows, then what? If A has two identical rows, then something happens. Teresa.
The first one, or it can't be true if they have.
What can't be true?
The determinant of A prime equals to the determinant.
Not sure what you're saying.
Because if you switch two rows,
yes.
then you do nothing.
Yes, that's right. That's right. So if you had this matrix with two identical rows, and you switched it, you would get the same matrix, right? That would say that the determinant of the switched guy is going to be negative the determinant of the original guy, right? Where this is the switched guy, although you can't really see it. Right? What does that tell you about the determinant? If you had such a matrix, its determinant has to be 0. Yeah. So this implies that the determinant must be 0. Right? Because the determinant would have to be a number that equals its own negative. Well, there's only one number that does that. Mia.
So if a matrix has two identical rows, the determinant's always 0.
That's right. That's right. Because of this above fact, right? Because because you know that if you switch two rows, you reverse the determinant.
Does the negative come from the -1 plus n plus like in the definition? You know how it's like, where is it? -1 to the row, the I plus j. Is that where the negative comes from in the determinant of A prime?
Yeah, it does. Yeah, we'll see exactly how it does, but yes, basically. Yeah. So yeah, we'll see it in a second. Okay. Statement number 3. If A prime is obtained from A by multiplying a row by some scalar, alpha, then the determinant of A, the determinant of A prime is going to be what? What do you think? If you multiply one row by some scalar, you scale one row of the matrix. What happens to its determinant? You multiply one row by 2. Yeah.
The determinant would be multiplied by alpha.
That's right. So the determinant of the new guy is going to be alpha times the determinant of the original. Okay. And why do you say that, Mia?
Because you can do the determinant by any row,
Yeah,
so it would have to apply to all the rows.
Yeah. Yeah, so you basically you do the cofactor expansion down that the altered row, and you'd say that, well, everything got multiplied by alpha. Okay, so right now, basically what we're seeing is the interaction of determinant with row operations, right? Switch, multiply. Right? We haven't. There's one more, but we'll do that next. We'll do that next time. Okay. So okay. So just as writing practice, let me write down the proof of 3. Okay. Right. So if you multiply one row, so suppose A prime is the same as A, but so with A's ith row multiplied by alpha. Okay. And we want to see that the determinant of A prime equals alpha times the determinant of A. Okay. So we just do what Mia said. Just take the cofactor expansion down that row, right? So take the cofactor expansion down A prime's ith row. Okay. You end up with the determinant of A prime is going to be AI1, AI1, AI2, AI2, AIN, AIN. Right. Where the primes indicate that these are the using the coefficients from alpha prime. Right? But AI1 prime is alpha AI1, right? It's the guy from A multiplied by alpha, right? It's a term from A multiplied alpha. What's the cofactor? AI1 prime. What's the relation between that and A's cofactor?
It's the same.
It's the same, right? Because the cofactor is going to be this -1 to the I plus 1 times the determinant of the minor matrix. But the minor matrix, if you erase the ith row, the minor matrices are the same, right? The matrices, these two matrices are identical, excepting that ith row, right? So AI1, right? So this AI1 prime is the same thing as AI1. Right? So we end up with alpha I2, AI2 plus alpha IN, AIN, right? Which is, whoops, sorry, which is just alpha times the determinant of A. So this is since Aij prime equals Aij, and since Aij prime equals Aij. Oops. Okay. Is everyone following? Anyone have questions? Anyone questions? So, right, we're just trying to prove this fact that if we multiply the ith row by alpha, then the determinant gets scaled by alpha also, right? And we do it by saying, well, look, take the expansion down that row. If we take the cofactor expansion down that row, we see that what we get is, well, this thing is just going to be alpha times the original term And then the cofactor is the same, right? Because the cofactor is just -1 to some power times the determinant of the minor. But the minor matrix of A prime and the minor matrix of A are the same thing, because we're going to eliminate the ith row, which is the only row that's different. Okay, maybe I've talked too much about that. Okay, so I'm not sure if we'll be able to finish this, but let's see. Okay, let's do the proof of number 2, which is maybe the only interesting one. So proof of 2. And we'll do it by induction. Do it by induction. Okay. So, in the case of 2x2s, right? In the case of 1x1s, it doesn't make any sense because there's no 2 rows to interchange, right? So you do for case 2, it's obvious. It's obvious. Right. The determinant of A, B, C, D is CB minus AD, which is minus the determinant of A, B, C, D. Right, so you just write it down. For 2x2s, it's obvious. So now, assume the statement is true for n minus 1 by n minus 1 matrices. Now, suppose A prime is obtained by switching rows I and R in some matrix A. So you're going to switch the ith and rth rows. Now choose a row K where K is not I or R. Okay, and we'll do what we're going to do is take the cofactor expansion of A prime down the kth row. Okay, so the kth row will be one of these unchanged rows. Okay, but the I and R guys are switched. Okay, so take the expansion of det A prime down down the kth row. Right? And what you get is, of course, you get A K1 AKJ summation J from other end. Right, the determinant of A prime is going to be, sorry, let me write this. Okay, and maybe you see what happens. Well, what's AKJ prime? Well, the kth row is the same, right? Kth row wasn't one of the rows that switched. So this AKJ prime, little AKJ prime, is the same thing as little AKJ. Right? It's going to be the same as in the original matrix. Right? Okay. Now what about the cofactor? AKJ prime is -1 to the k plus j times the determinant of mkj prime. Here's the key part. I know you're tired. This is the last thing you need to see. What's the determinant of mkj prime? The determinant of mkj prime. So remember, we got a prime by switching the I and R throws. Okay, and now we're going down the k throw, which is not the ith or the rth, right? And we're looking at the minor matrices you get by crossing out the k throw and cutting like this. So what's the determinant of mkj prime? And remember that these guys are n minus 1 by n minus 1 matrices, right?
Is it just negative mkj?
Yeah, it's going to be negative the determinant of mkj. Right? Right? And so what you get is negative the corresponding cofactor. Right? So you end up with negative 1 times the corresponding cofactor, and so you end up with negative 1 times the determinant of the original matrix. Okay, so that's maybe we'll stop here. We'll stop here. Okay, see you. Any questions? Any questions?